So let's go through these work solutions for electrostatics. Problem 1, which was calculate the charge carried by 3 times 10 to the 9 protons. So our data, now the charge of a proton I've taken from the data sheet because the charge of an electron is negative of this value and a proton has the same magnitude but opposite sign. The number of protons is given, so I'm just going to use a capital N to represent number. And what we're after is the total charge of carried by all of these protons. So I'll just give that Q as a sign, as a symbol. To calculate what that is, well, it's just a matter of the charge of one proton times how many protons there are. So, which gives us, okay, problem 2. We've got calculate the number of electrons that make up a charge of negative 3 coulombs. So that's the total charge. And I want to know the number of electrons there are, and I know that the charge of one electron as per the data sheet. So it's just a rearrangement of this, isn't it? So we want the number of electrons is Q divided by the charge on one electron. These cancel, so we end up with a number. Okay, that's it for the first two. So problem 3, we've got an alpha particle consists of 2 protons and 2 neutrons. Calculate the charge on an alpha particle. So the charge on one proton is, the charge on a neutron is 0, they're neutral. We have how many particles all up? We've got, well, there's 4 particles, but there's only 2 protons. So the number of protons is 2. So we want to find out the charge on the whole alpha particle. Okay, so I'll just give it a symbol. That's A for alpha. The charge obviously equals how many protons we have times the charge of the proton, which gives us 2 easy. So question 4, calculate the magnitude of the force applied to an oil drop carrying a charge of 3 millicoulombs in a uniform electric field of 7.5 newtons per coulomb. Our data, well, it says calculate the magnitude of the force, so we want the magnitude of the electrostatic force. The charge, we know, the charge of the oil drop is 3 millicoulombs, so we need to convert that. So I normally just times it by, if it's milli, that's a thousandths. So it's simply times 10 to the minus 3 coulombs. So the electric field strength is given. Okay, so our workings. What do we have here? We have force, we have a charge, and we have an electric field strength. So if you're looking at your formula sheet, which I'll get up on the screen. Okay, under electricity and magnetism, this is our formula here. So F equals QE. So this step in problem solving of identifying the known and unknown variables is useful for figuring out what formula you use. Okay, so we put our starting formula and we substitute and solve. Okay, notice our units cancel out and we're left with newtons, which is the correct unit of force. So in answer to our question, the magnitude of the force is 2.25 10 to the minus 2 newtons. Now, it didn't ask for direction, but a general statement, if it did, would be something like the direction of force will be in the same direction as the electric field. That is from positive to the negative plate, if we're talking about between parallel plates. So question 5 asks, calculate the work done to move a positively charged particle of 2.5 10 to the minus 18 coulombs a distance of 3 millimeters towards a positive plate in a uniform electric field of 556 newtons per coulomb. So the work has to be done against the field because you've got a positively charged particle and you want to move it towards a positive plate where it normally wouldn't want to go. Our data, the distance needs to be converted from millimeters to meters. So again, times it by 10 to the minus 3 to convert to meters. Electric field strength. We want to calculate the work. So look at the variables we have. We want W, so we want a formula that calculates work. These are the variables that have been given to us. So if we check the formula sheet again, we are after this one here that says work equals QED. Okay, too easy. So we write the formula as shown. And this one is just a matter of substituting in. Okay, so QED. Notice, before I move on, QED is force, isn't it? So QE is force. And we've got force over a distance or a displacement. So that reminds us of this formula for work. Work is force over a displacement. And the answer? So the answer we get is in Newton meters. And 1 Newton meter is equivalent to 1 joule, because work's also measured in joules. So it's equivalent to this in joules. Our final statement would be the work done to move the positively charged particle towards the positive plate is 4.2 times 10 to the minus 18 joules. So question 6 was, an electron gun accelerates an electron a distance of 12 centimeters between a pair of charged plates across a potential difference or voltage of 15 kilovolts. What is the magnitude of force acting on the electron? So it's just showing that an electron has been accelerated across some parallel plates, and we need to calculate the magnitude of the force. Now this one we will find involves 2 formulas, so it is the level of complexity is slightly higher. So let's see what data we have. We have a charge of an electron, the distance between the plates, making sure that we convert it, the volts, making sure again that we convert it. So again, okay, so we want force, okay, so the electrostatic force. Do we have enough here? So normally, you know, the equation for force is F equals QE. Well, we don't have E, but we do have these values here. Okay, so what from there can help us to determine what the value for E is? Okay, let's look at our formula sheet. Okay, looking at the variables we've got, to calculate E, if we've got voltage and the distance between the plates, then we can use that equation here. Okay, and then once we've got E, well, we know what Q is, so we can calculate the force using this other equation. So that's our 2 steps. So it's problem solving involving 2 formula, which happens quite a bit in physics. To do that, we need that first. So let's calculate the electric field strength using this equation, substituting using our correct converted values. Okay, so here's another unit for electric field strength. We saw in the previous example newtons per coulomb for electric field strength. So 1 Newton per coulomb is equivalent to 1 volts per meter. Okay, it's the same thing. So we'll use these units for the next part. So we're going to use this equation, and because we've got charge in coulombs, that's why we want this value, these units for electric field strength. Let's say newtons per coulomb. So you can see cancel, we're left with 4 newtons, which is the correct unit for force. And that will give us a negative value in newtons. Okay? So the negative sign indicates that the force acting on the electron will be in the opposite direction to the electric field. It did only ask to calculate the magnitude, which is that, but if it did ask, then you would say, you know, it's an electron, therefore the direction will be towards the positive plate, which is in the opposite direction to the electric field. Electric field goes from positive to negative. The electron will move towards the positive plate. So problem 7 starts moving into Coulomb's law. So we've got 2 particles a distance apart, and we want to calculate in the first example the force. So we've got 2 particles, charge 1 and 2 have charges 6.0 10 to the minus 8 and 8 10 to the minus 8 coulombs respectively, and they are 15 centimeters apart. What's the force between them? So let's get our data down, and we are after the force. So for this problem we'll need the Coulomb's law equation, and make a note, we've got the charge values, we've got the distance between the charges, but we need to get the constant here from the data sheet. So we also need to grab this value here for the electric permittivity constant. So let's write our formula as shown in the data in the formula sheet. Okay, when you have a square in the problem, that's so easy to forget to square that value. So just, you know, keep reminding yourself, you know, to double check when you substitute it in. And also, because we've got a lot more values here, just be careful with the calculations. It's easy to type in the wrong values. So our answer should be, and because the charges are the same, they're both positive, we have repulsion. So the question asked you to calculate the force. It didn't say just the magnitude. If it asks you for the force, then you should probably also provide the direction. So when you go to state the direction, you know, if the charges are the same, it's repulsion. If one's positive, one's negative, then opposites attract. So in that case, it would be attraction. Question 8 is very similar to the question 7, except we've got 1 positive and 1 negative charge. So the force will be attractive. So I won't really talk through this one. I'll just show so you can check your workings. Again, making sure that you squared this value here. We determine pretty much it's attracting because we've got opposite charges. That is, opposites attract. The workings for question 9 are similar, but I've put it in because we've got some values that you need to convert, and these are often overlooked by students. So we've got millicoulombs and microcoulombs. So you need to be able to convert from milli and microcoulombs to coulombs. So in this one, I'll just point out the conversions again. So it's millicoulombs, so we need to times it by 10 to the minus 3 because it's a thousandth of a coulomb, and the micro is a millionth, so we need to times it by 10 to the minus 6. If it was nano, it will be times 10 to the minus 9. Okay, again, make sure you convert the distance between them, and over here that you've squared that distance in the calculation. So the final answer should be 3 times 10 to the 4 newtons, and it's attracting because we've got a negative charge and a positive charge, and they attract each other. So question 10 is slightly trickier, but easy to work out if you set out the problem systematically. So we've got two identical charges, so Q1 and Q2 are both equal in charge. Now the force between them is given. It says it's repulsive, so this agrees with this. If they're identical, they're the same magnitude and have the same sign. If they're both positive or both negative, there will be repulsion. So the distance between them is also given. It wants us to calculate the charge on these particles. Okay, and because they're identical, we just need to manipulate the formula just slightly. Okay, so the data so far, we're given the force, we're given the distance between, making sure we convert this to meters. We know the constant, and we want to find the charge on the particles. So we've got Q1, and it's identical to Q2. Okay, so these are both the same. We want to find out what they are. So in this equation here, we've got Q1 times Q2. If we say, okay, let's say because they're identical, we can just say Q squared. Okay, and we can substitute that in. Okay, and we substitute all our known data into this formula. This is what we're trying to find out. So we want Q squared on one side, and we want all this other stuff over to the left side. So that means we'd need to times both sides by that and by that, which will leave just Q squared on the left side. If I just show you using this formula, so we will be doing times both sides by this and by this and times that. That gets that on that side, and then we'd be left with Q squared on this side. So I'm just going to swap them over. And to find Q, which would be, you know, Q would be the same for these. So all of these equal Q. So I need to take the square root of this. So I'll do that over here. And that should give me a charge of 2 times 10 to the minus 10 coulombs. So therefore, Q1 equals Q2 equals Q equals 2 times 10 to the minus 10 coulombs. And that's it.